and we'll go from current slide. Okay. Now, let me just make sure. Still just 6 students here. 1, 2, 3, 4, 5, 6. I was hoping for more than this because we've got a lab today, but maybe they'll be coming in a bit. Any questions, concerns, anything up till now?
I have one.
Okay.
So I was able to start my observation last night.
Good. Excellent.
I kind of got a little confused on the chart that we're supposed to do.
Okay.
Can you explain how we're supposed to do that chart again?
Okay. It's not the 2 questions at the bottom of one page. It's the chart at the top of the next page, right?
That is correct.
Okay. All right. Now, let me just ask you, you saw the moon last night, right?
Yes, sir.
Okay, can you give me a quick description of how it looked? Okay. Well, between the two of you, give me it's what?
Hold on, I'm trying to grab my notes. I'm sorry.
Well, was it a full moon?
No.
No. Was it?
Gibbous, waxy, I want to say it was like.
Okay. So it was a little bit larger than half a moon. Is that right? Hold on. Juan's coming in. Let me get him here. Juan is here. There he is. Okay. All right. So let me just make sure I've got everybody. That's 7 students. That's right. 1, 2, 3, 4, 5, 6, 7. Got it. Okay. So you were just over half a moon, right? And that was your first day of observation. Now you can either call that day 0 or day 1. I don't care which one you call it. Okay. Now, on your chart that you saw there, the very bottom down here would be a new moon that you see nothing of it. And then at the top, 1 would be a full moon. So if you were just over half moon, you would start right about there. And depends on whether you start at day 1 or day 0, you'd be right there. Now, in 2 nights when you see it again, it's either going to be getting bigger or it'll be getting smaller. So the next one will be a point either up from there or down from there, but then over 2 days. Does that make sense?
Yes, sir. So the fraction illuminated is the actual sunlight that we see on the moon.
Yes, that's exactly right. Right. And if you said it was gibbous, meaning it was a little over halfway, is that what you meant?
Yes, sir.
Okay. You agree, Roy?
I was more 3/4. What about you, Roy?
I don't know. He doesn't seem to be hearing us now. He was on here before, but not now. Okay, if it's 3/4, then move up, past halfway, in between halfway and 1, and do about 3/4. And if you started day 0, then be right on the y-axis. If you're starting day 1, then that first block over. And then in 2 days, when you observe again, it's either going to be bigger or smaller. So you go either up or down from there. Cormisha's here. Let me get her here. Okay, but what she was asking about was the size. Would you say the size was half moon, 3/4 moon, something in between?
It was the moon was showing on I guess the northern side of the moon.
Uh-huh.
Where I was, and it was about a little over half moon.
Okay. All right. Okay, so you got what to do on that graph then. The graph has it's sort of like this, right? Vertical axis is the fraction of the moon, horizontal axis is how many days. Now if you called that day 0, you start right on the y-axis, the vertical axis, okay? And you go up, if it's just over half moon, just over halfway up, okay? And then In 2 days, you'll be over here somewhere, and it'll either be a little bit larger or a little bit smaller. So the next point will be there. And you plot that every day you see it. It's either a little bigger or a little smaller, but you move over the 2 days or 3 days, however long between your observations, you do that. Does that make sense? All right, good deal. Good folks. Now, and I'm guessing y'all were viewing what, about 10 o'clock at night or 9, 9:30? When?
Mine is about 10:30.
10:30. Okay. So, say again?
Same.
Same. Okay. Okay. Y'all are night owls then. Okay. All right. So, folks, you should be able to see the moon. So if you haven't started your observations, try to start them tonight. Now I'm looking out at the sky right now and it's very cloudy. Okay. If that continues through this evening, you may have a tough time. But in case it does clear up, try to get out there tonight and do your first observation. Those who made your first observation last night, then you skip a night and try again tomorrow night. Now, if it's cloudy, then do the very next night. You try to skip at least one night in between, but no more if you can help it. Sometimes you can't help it, so the very next good night, you get your next observation. Now, if it's pouring rain, probably don't go out there, okay? But try to do the same time as you did the first observation. Every observation from there on. And then I heard some pretty good descriptions of where it was in the sky, and remember, your first question talks about landmarks. So if you have, oops, here comes Don. Don is coming in. Okay. So, what was I saying? Um, yeah, the landmarks. If you've already got that plotted out, I hope you have. You had plenty of time to do that. Found your spot. Make sure you go to the same spot. And where is the moon relative to the landmarks? And just have them spaced around, maybe 3 or 4 on the north side, 3 or 4 on the south side, or whichever way you happen to be facing. 3 one way, 3 another, something like that. And then, is the moon closer to the telephone pole or the big oak tree or whatever, in between the two, whatever. And if you can, like Roy just said, if he was having directions with it, if you have a good idea where north is, and where I'm sitting in my bedroom here, it's a bedroom that we're using as an office, I'm facing almost due north. So if I were going to be making the observations, I would say, I would use that. If you have a compass, use a compass. If you don't, if you know where north is, make a good guess at it. I'm facing basically almost due north. So that would make it fairly easy for me. Some of you it may not be so easy. So whatever you're using, then tell where the moon is relative to the landmarks. And I'm just going to make a guess now. Roy or Valerie, either one, would you say the moon was just shortly over the horizon, or was it up a ways when you saw it last night? Okay, I figured that's where you would have been starting. So the next night, it's probably, I'm guessing, going to go up a little higher, because the reason you couldn't see it night before last, it was below the horizon. So my guess is it's going to be going up some, and it'll either be going to the west, to the east, to the north, to the south, something like that. So it's moving from this one to that one to that one. So that's what your first description is. Where is the moon going relative to the landmarks, your trees, your power poles, your whatever it happens to be, the sign, the road sign, whatever it is you're using as your reference. Your second question, and last night was your ground. That's where you're starting from. And then the next question was, could you see any stars last night anywhere close to the moon? Yes. Okay. Was it a pattern that you think you can find tomorrow night as well? Okay, well, try to get you a pattern of stars somewhere close to the moon. It doesn't have to be right at it, somewhere close, and then from that pattern of stars, mark where the moon is going. And again, if you can do east, west, north, south, something like that, that would be great. or if it's moving to the right of those stars or to the going above the stars, below the stars. Again, wherever the stars are, that pattern of stars, that's what you do your second observation on. And then the third observation is the size of the moon. And that's the one we just talked about. Does that answer pretty much? Great. And the rest of the lab, hopefully all of you have done, but once you get your, I don't know, they say every other day for about 2 weeks. So you won't be able to, I don't think, get more than 7 observations. If you get 4, 5, 6 observations, you'll be doing pretty good, probably. So do the best you can with what you got. Okay? But every other day, unless one's a cloud out or a rain out, and then the very next day that you can get out there and see it, go for that one. Okay? All right, excellent question. Any others, by the way? All right, let's go over then a little bit of what we're doing today. Okay, we're starting in chapter 19, which is building the Earth's surface. Okay, we got a decent start on it last time. We're in 19.3 right now. We've still got to finish 19.3, do 19.4, and basically I think we probably will finish 19 today and may even have time to get started in 20. So I don't know. I think I'll just hold off and pull up 20 later. It'll be a pain in the neck to do so, but we'll wait and do that. And so what we're going to do is work on 19 today. Now, you're going to stop me at 4:15 today, because at 4:15 we're going to do the lab. Now, I put the lab out there. I put under content, I put the laboratory simulations. Did any of you fail to find that? If so, I'll show you exactly how to get to it when we go to do lab today. I'll do it on my blackboard and let you see every step I take. Okay, now, did any of you try to open that lab? Or are you just going to wait till the day to do it? Okay, that has happened before. This is the only simulation I could find that had anything to do with plate tectonics. But it was one of the simulations that when I taught the Physical Science 2 last spring, and we had to go off campus and I had to start doing virtual labs, I only found out because the students told me. Yeah. Oh, no problem. I found out then that a bunch of the students could not open the simulations that had what looked like a coffee cup with hot coffee in it. I can't describe it any other way, but I'll point that out when we get there. Several of them could not open that. I sent them to the IT people. They tried to work with them. There's just no way. There was something about the Java they had on their computers wasn't compatible with the Java that was required to open that. Now, I don't know enough about Java. I know it's some sort of machine programming, and evidently something wasn't meshing. So therefore, since this is one of those labs that some of you may not be able to open, please be here for lab, because I'll be doing it, because it will open with my computer. I will do the entire lab with my computer, recording it on Screencast-O-Matic. It will go out there on YouTube video, so anyone who's not here today, if they can't open the lab and do what was directed, then they'll need to go to the YouTube video and do it there. And we're going to do it as a group, unless y'all want to do it individually. But since maybe a few of you will be able to open it, some of you can't, we're going to go through the whole lab that way. Now here's somebody coming in. That's one. I already let him in once. Evidently it kicked him out again. So one, yeah, is already counted present. Okay. Now, did all of you see the lab out there on under message, the worksheet? Yay or nay? Okay, you did. Okay, I want to make sure it showed up. Okay, because I sent a test to one of my calculus classes, and some people could open it. They could all open it, but some could read the integral signs and some could not because they had different versions of Word. So I wanted to make sure y'all all had the version of Word that could read what I put out there. So if you could, fantastic. Probably a good idea to have copies of that so you can be filling in the labs when we are doing them. So if you can have ability to print those labs, that lab might not be a bad idea to do so, okay? But if you don't have that capability, you can just fill in the answers like some of you have been doing, and that will be fine too, okay? So, any questions about how we're going to proceed today? Chapter 19, Building Earth's Surface. Now, we'll go to 4:15. At 4:15, we'll do a timeout, and we'll start the lab. That'll be basically the lab for Chapter 18. Okay? Then, when we finish that lab for 18, you'll be through for the day. And then, more than likely, we will have already finished 19 and got started on 20. Okay? So that means sometime after class today. Now, immediately after class is over, I've got a meeting that's actually starting at 4 o'clock. I can't be there at 4 because we're going to be finishing chapter or working on things and starting a lab at 4:15. So I told her I can't be there. So as soon as I do get out of the class, I have a meeting. So I'm not going to have a lot of time tonight to work up the next lab, but I'll try to do that tomorrow afternoon and try to get a lab for this chapter. I can't remember if the one that we did in class will work for here. I think it may be it will, but if it won't, I have to make up a new lab for this one. So we'll just see what happens, but we'll get going. And then also, I think the test for chapter 18 was also out there on Blackboard Message, was it? Good. Okay. All right. So if you haven't checked on that, the Chapter 18 test is out there as well. So we'll be doing the lab at 4:15, and then anytime after that, you can do the test, send it back. You have at least a week, more if you need it, but at least a week to work on that. Okay. Now, any more questions before we get started on Chapter 19 where we left off before? All right. I did notice here a really good slide or figure in the book that was not in the slide set. And I can't begin to draw it, but we've talked about it, so hopefully when I hold it up to the camera, you can do it. And now that I've got my microphone, I won't be blocking my sound any, okay? So here is the figure. Okay, that shows an earthquake. The location of the quake way down beneath the surface, that's called the focus of the quake. Directly above that focus on the surface is what we call the epicenter of the quake. Now, they don't show that really all that well here, but they do show the waves, the seismic waves going to a station somewhere. Now, this is a long way away because you see the curvature of the earth. You don't see the curvature of the earth anywhere close. That's a long, long way away, and that shows the P waves getting there first, and those are the red squiggly lines on your seismograph there, okay? Then, sometime later, the S waves get there, and that's, okay, I'm sorry, I've got it backwards. They show the S waves on top and the P waves on bottom. Why did they do that? Oh, no. They show them both on both of them. Sorry about that. Okay. The P waves get there first, S waves get there second. Okay. And then the surface waves get there third. Well, the red on the squiggly lines, that's the P waves, showing them getting there before the S waves. Remember, P means primary or pressure. Okay. Longitudinal waves. Those go through everything. The S waves only go through solids. Those are secondary waves, shear waves, also called transverse waves. And then the surface waves get there last. They're actually the biggest, they show up the most, but that difference in time between the P waves and the S waves, that determines the distance that station is from the earthquake. Okay? And this shows two states. The first one shows a station not close, but closer. This one shows one way, way further away, and showing both the S waves, P waves, and ultimately the surface waves getting there. Okay? And that difference between the P and the S, that time difference there, that determines how far you are from the waves. That was the last slide we talked about. Oh, wait. I wasn't paying attention. Two people were waiting. So let me admit both of them. That's Nikaya, which I think I already had here, didn't I? Yeah, I had Nikaya here. And who was the second one? Who was it? Harry. That's right, it was Harry. Because I didn't have you here before. Okay. Now my pen won't write. Okay. So that's a total of, why won't it show me a number here? Okay, 10 students. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, got it right. Now, why in the world doesn't give me any opportunity to close this? Oh, that may be it. Nope. What is it doing here? I don't know. Yuck. I've never had this happen before. Okay. Okay, how do you get this to reduce? Ah, there we go. I just hit something and it went. All right, any other questions before we get started today on Chapter 19? Okay, we found out how to measure the size of an earthquake. That's with seismographs. Okay, how to measure the distance from an earthquake. That's using triangulation with 3 different sites, and the difference between the P and the S waves, that tells you how far each site is from the earthquake. Now we're going to figure out how to measure an earthquake's strength. Okay? Now there's been a couple of different things tried or done historically. The first and the earliest was they just measured the effects of the earthquakes. So in other words, if you had a huge amount of structural damage to buildings, they called it a really powerful earthquake. If you had fires and landslides, disturbance of land surfaces, tsunamis out in the ocean, if you had any of those things, the more severe they were, the more severe they said the earthquake was. And one of the scales they used, they probably had several, but one was the Mercalli scale, and that was just relative intensity of the effects of the earthquake. So on level 1 on the Mercalli scale, you couldn't even feel it. They registered there was an earthquake somehow, but you couldn't feel it. Up to 12, and that's total destruction, visible ground waves, those surface waves were visible, wiping out everything in sight. The most powerful. Okay? Now, the problem with the Mercalli scale, it's all based on the damage assessment. Okay? Now, I'm going to give you an example of why Mercalli scale was not a particularly great scale to use. It gave them a measure. Let's see if they say anything about it here. Oh, I can't advance until I click on the slide and then I advance. Okay. No. We'll come back to that later. Here's a reason the Mercalli scale is not particularly, I don't want to say not useful, but not the best of scales. I'll just leave it like that. And here's why. I can't remember how many years ago now. I would say between 6 and 10 years ago, right very close to Christmas time, there was a pretty major earthquake that hit really hard on the island of Hispaniola, which Hispaniola is split between Dominican Republic and Haiti. It especially hit Haiti really, really badly. Do any of you remember that earthquake? There were many teams that went out afterwards trying to help repair damage and stuff like that. Anyone remember that? Like I said, it was, I'm guessing, between 6 and 10 years ago. No one remembers it? Well, anyway, Port-au-Prince, which was the capital of Haiti, I mean, that was almost, it was awfully close to the epicenter. So the destruction was massive. And Haiti is the poorest country in the Western Hemisphere. Not the poorest in the world, but in the Western Hemisphere, poorest country. And it destroyed homes, it destroyed buildings, it destroyed apartments, it destroyed business, it destroyed, I mean, it just was really bad. So if you were measuring that on the Mercalli scale, that would have probably registered probably up at 10, 11, or 12 on the Mercalli scale, because it was widespread destruction. Now, two reasons. The first reason I already mentioned, it was really close to the epicenter. So you had enormous amount of damage because you're right there at it. But the second reason had nothing to do with the earthquake. Like I said, Haiti is the poorest country in the Western Hemisphere. And as such, they had terrible, terrible building codes. Almost maybe non-existent. If you want to throw up a structure, you throw up a structure. Most of the buildings there were concrete block structures. And if you've ever been in a concrete block structure, there's just not a lot of structure to it, okay? Yeah, concrete blocks are solid and rigid, but hey, you have an earthquake, they either break or they come apart at the seams, the mortar joints and stuff like that. Not the best place to do, and that's why they had such terrible destruction there. Okay? Within, I can't remember exactly, but it seems like it was within 2 or 3 months, there was an earthquake down off Chile in South America. And again, it happened in the country, not off in the water, in the country. But Chile, because it's on the ring of fire in the Pacific, they had extremely good, stringent building codes. So their buildings were all steel reinforced, everything they needed to do. Now, I'm not saying all, I bet you some homes weren't up to code, but most of the homes were up to code. Everything was done much more carefully because they had a bigger history of earthquakes. Well, guess what? The damage in Chile was major, but not nearly what it was in Haiti. It wasn't the fault of the earthquake, because the next scale we're going to look at actually measures the strength of the earthquake. The one in Chile was between probably 2 and 10 times more powerful than the one in Haiti, but the destruction in Haiti was far worse. So the Mercalli scale is not particularly good because it's just a relative intensity. In other words, how bad was the damage compared to what it could have been somewhere else? I mean, not somewhere else, just, how bad was the damage, the physical damage. Guess what? If that same earthquake had happened out in the middle of the island, no, it's a small island. So let's say it happened in Siberia, where almost nobody lives. It's way out in the boonies, and there wasn't a lot to destroy. It may have destroyed a bunch of trees or things like this, but it just didn't do that much damage. Same earthquake would have been on the Mercalli scale 2, 3, 4, 5, something like that. On the Mercalli scale, the one in Haiti, because it was right under a very big population center, the capital of the country, and their building codes were so terrible, it made total destruction. Okay, so therefore, Mercalli scale is a bit too relative. Okay, now this next slide does show up in your book at the top of page 492. So I don't believe that many of us are probably going to have too much opportunity to be around when an earthquake happens. I may be wrong. Maybe you'll be living in a portion of the country where they would have them. Or maybe a part of the country where you're living will suddenly have one they're not expecting. But if you are around, these are pretty good guidelines for just about any emergency. During the shaking, like when it first happens, number one thing, don't panic. Now that's easy enough to say from afar. We're not in an earthquake, we're nowhere close to one. Say, oh yeah, don't panic. Well, guess what? If the ground started shaking, my house started shaking right now, I think I'd be pretty close to panicking. I'm up on the second floor, you know. I don't want to be up here if that starts. So, well, I'll try not to panic. Okay. Now, interesting. If you're indoors, stay there. Because if the house has already fallen on top of you, then the odds are it probably won't. Okay. But seek some additional protection if you can get under a good heavy table or even a desk. Possibly if you have room under a bed, that might be okay too. Or if not, in a doorway. Doorways typically have more reinforcing there than an open wall would have. Okay, so a doorway would be better than out in the open. Okay, stay away from glass. I'm sitting right in front of windows here. I'd want to move back and get under that doorway. Okay, or maybe even better, get under a table somewhere else in a different room, but interior. Okay, now they say don't use, okay, let's just imagine the power goes off, and let's imagine it's dead of night, so it's perfectly dark. Don't strike a match. Okay, now I don't know about where you live, but in our house here we have gas heating, especially in the downstairs part, and we have gas stovetop. Our oven is electric, but the stovetop is gas, which means downstairs on the main floor and in the basement, they're gas lines. Okay, if there was serious enough shaking and breaking, some of those gas lines might rupture. And pitch black at night, I light a match just to see where I am. Way. If that gas has made it up to wherever I am at that time, that could cause an explosion. You don't want that to happen. Don't light a candle to see. If you don't have a flashlight, figure your way. Find your way around. Good idea to keep a flashlight or working flashlight handy. Okay? Or any other open flames. Don't have any. If you had a fire in the fireplace, put it out. Get water and dump on it. I might make a mess. Don't worry. You don't want to catch your gas line on fire. Okay, so that's number 2. Number 3, what if you're outside? Don't move inside. Stay away from buildings. Move away from a building. In my backyard, I would go out somewhere far enough from the building, from the house and the shed and the garage and everything else, so that I don't risk anything falling on me if it should happen to start falling down. So if you're outside, move away from buildings, move away from power lines. I have a power line coming from our transformer there right to the house here. Want to get away from it. Don't want to get near the back fence because the power line going up to the transformer is across that back fence. Don't want to go there. Stay in an open part of the yard. Okay. Stay in the open. Probably not the best idea to get under a tree, because the tree, if it had some weak branches in it and stuff, if it did enough shaking, it could start dropping branches on you. You don't want that to happen. Okay, so try to get out in the open if possible. Okay, now if you might feel like, hey, this is a brick wall here, that would be safe to be near it because it's strong, or a fireplace or something like that, the chimney going up on the outside. Don't, because if it's a big enough shaking, some of those bricks may fall off onto you. Get away from the building. Okay, don't run through or near buildings. So it says near buildings. Now I'll give you an example of why that's the case. It's not a great example. It has nothing to do with the earthquake. But when I was a sophomore in college, the summer between my sophomore and junior years, I was in Navy ROTC, that's Reserve Officer Training Corps. I was on my third class midshipman cruise that summer, and we went up to Little Creek, Virginia, got on an old World War II vintage amphibious warfare ship, and the name of the ship, the title of the ship was an LSD. That stands for Landing Ships Dock. And my dad got such a kick out of telling everybody when they said, well, where's Charles this summer? He said, oh, he's on an LSD trip, and that's was funnier back then than it is now, but it didn't seem that funny to me at the time. Okay, but anyway, I was in the Navy, on my cruise. My older brother was leaving to go on his first class cruise because he was in Navy ROTC as well. But my younger brother was, I think, probably between his junior and senior years in high school, and he didn't want to go up to, when my folks took my older brother up to catch the flight, because he was flying to Rota, Spain to catch his ship that was going to sail around in the Mediterranean for 4 to 6 weeks. I was just crossing the Atlantic Ocean and coming back. I didn't get to go into the Med. He did. He was a first class midshipman. I was a third class midshipman. There was a big difference there. Okay. Well, my younger brother went to spend the night in town because my parents were going to be really late coming back, with a friend of his, and they were just tooling around in town, and they happened to hear the fire trucks. So they decided, hey, let's go see what their action is, because Waynesboro, Georgia, there's no action at all. So they followed the fire trucks. Volunteer fire department, by the way. Well, sure enough, some old houses, some of them abandoned. One of them had caught on fire. I don't know how, but it had. It maybe they had squatters in there living there and were burning pieces of furniture or something in fireplace. I don't know why, but it caught fire. There were some houses nearby, and they were close together, that had people living in them. Well, the fire department was trying to put out the fire there, so Dan and his friend, and this is really good of them, I wouldn't have guessed they would have done it, they started helping those people move their furniture out of their house so that if their house did catch on fire, they wouldn't burn all their belongings. So they were doing that while the firefighters were fighting the fire next door. And the firefighters had about gotten it under control, and Dan and his friend started helping the people move the stuff back into the house. And Dan was walking between the two houses, the one that had just burned and the one they were helping. And about that time, one of the volunteer firemen, who wasn't too bright, decided, hey, it's sort of cool to watch the water make steam off that chimney. So he started spraying the chimney with that high-powered fire hose. And sure enough, it was steaming up and making quite a show. Well, the chimney had been weakened by the fire, and the chimney fell on my younger brother when he was passing between the houses. Okay, not a good story. Okay, it knocked him out. One of the bricks hit him in the head. It probably broke the brick, knowing my brother, but never mind. But several of the bricks where the hot side had been near the fire landed against his leg, his none too much on the upper part of his body, mostly his lower part. And so he had some third-degree burns on his feet, legs, thighs. I think that's about as far as it went. And but he was knocked out, so he couldn't get up and leave. Well, someone saw it happen. They dug him out. They got him out. They rushed him to the hospital. But because neither parent was in town, they couldn't do anything to him unless they got permission from a parent, because he was a minor. So he was in agony in the thing until they were able to get in touch. And this was before cell phones. Finally, they got in touch with my parents. They gave him permission to give him something for the pain. And anyway, that was the story. The point is, even if it looked like a strong brick fireplace, if it's been damaged by the earthquake and there's an aftershock, it could come tumbling down. So stay away. Don't go through or near buildings. Okay. Now, if you're in a moving car, stop it. Okay, as quickly as safely possible, but stay in the car, because guess what? The car suspension is going to absorb some of the shaking. If there's a second aftershock and things like this, it's actually going to be better. Now, I wouldn't say pull underneath a highway overpass. No, don't do that. Remember, I think I mentioned the earthquake that was in Los Angeles just a few months, it seems like, after the one that was in San Francisco during the World Series. The one in Los Angeles made roads collapse on each other, okay? So don't pull underneath an overpass. Get out in the open, but stay in your car, okay? Probably get off the highway because you don't want to be in the way of emergency vehicles, but pull off to the side, stay in the car. You're probably safe there. So that's during the shaking. After the shaking, it says check but do not turn on utilities. So even if the power went off, the gas went off, all like that, if you do smell gas, or even if you don't, but especially if you do, open as many windows as you can, open as many doors as you can. If you know where the main shutoff valve is for your gas line, get down there and turn it off. Leave the building as soon as possible. Report the leak to the utility company. Do not re-enter the building until it has been checked out by professionals and they're sure. Now, if water mains were damaged and you see water spraying up somewhere, if you know where that main valve is, turn it off. If electrical wiring is shorting out, if you know where your meter box is, go down and turn that off. Now, this is all assuming you know where these places are. So do that, okay? Then get out of the building, okay? Go to a radio if you have one that's battery operated. If it's electrically operated, if the power's off, you aren't going to do it. Radio or television are only good if you can get to them. And listen out for emergency bulletins. There may be aftershocks, there may be emergency somewhere in your area you want to stay away from. Stay off the telephone except to report those emergencies like the fire, the gas smell, those kinds of things. Don't get on the phone and say, hey, Grandma, are you okay? I mean, you want to know that, but guess what? The phone lines are going to need to be reserved for emergencies, okay? Now, cell phones, you might say, I'm not going to bother anyone being on a cell phone. Well, if cell towers have come down, then cell phone service may be very restricted as well. And if those have been cut, some of the cell routes have been eliminated, yeah, stay off the cell phones as well. Stay out of severely damaged buildings because there can be aftershocks, and if there were enough shaking going on and an aftershock comes, what just shook before may fall now. Okay, so stay out of damaged buildings. Don't go sightseeing. Now, this happened back when some of the weather emergencies happened. The tornadoes that happened here in 2011 and other times like this, people went out to see, hey, I heard it was really bad down around, Pleasant Grove. Let's go over and see what happened, No, don't do that, because you may be hampering emergency personnel and repair crews from getting to where they need to go. And you don't need log jams of sightseers in the way. It's bad enough people who lived in the area shouldn't be going there, but certainly sightseers should not be going there. So those are just a few of the guidelines they give for it. Okay, they're mostly just common sense things, but in case you hadn't thought about some of the ramifications, think about them. Okay, so there's Mercalli scale and what to do. This is sort of mixing at a bad place, but I guess they had to put it somewhere. Let's go to the current scale. This is called the Richter scale. And by the way, a potential paper topic would be, who in the world was Mercalli? How did he come up with his scale? What are the pros and cons of his scale? You know, there's several paper topics there. Here's one. This one would be, who in the world came up with this? I'll give you a hint. His name was Charles Richter. He was a seismologist, someone who studied earthquakes. Guess where? California Institute of Technology in the early 1930s. Hey, where is the San Andreas Fault? That's called most of the earthquakes that we have in the continental U.S. California mostly. So no surprise he was there at Caltech. Excuse me, I got hiccups now. His scale is based on the swings of the seismograph recordings. So this is going not on how much damage was done, like the Mercalli scale. This is going on how much energy that earthquake is registering on a seismograph. Okay, seismograph is something that measures or graphs the movement of the earth based on that. Now, the Richter scale is what they call a logarithmic scale. And here is just sort of an example of that. They give you three numbers here, 3 and 9. Okay, 3 on a log scale, that would be, I'll get into a little more detail on this later. That would be something 10 raised to the third power. So what you're measuring is something in the thousands. That's the amount of energy recorded in this earthquake. Whereas a 9 would be a 1 with 9 zeros after it. 3 would be 1,000, 6 would be 1,000,000, 9 would be 1,000,000,000. So this would be 1,000,000 times stronger than a 3. A 9 is 1,000,000 times stronger. It's not 3 times stronger, it's 1,000,000 times stronger. It's how many zeros are represented by that exponent. 10 to the 9th as opposed to 10 to the 3rd. You have 6 more zeros, that's 1,000,000 times stronger. And a 9 is the largest measured earthquake so far. And at least one of those 9s was in Alaska, but way back, I'm guessing around the 40s or 50s. And it was in a part of Alaska that was very uninhabited. It did a major amount of damage. Here's Scott coming in. Let me get Scott in the class. All right, Scott's here. Well, he's partly here. My pen is not writing too well. You may be right, because there are faults that go through Alaska, and usually right. Well, there's usually not that much vertical movement, but it does show a weakness there. But think about this too. Where was the gold rush of 49? San Francisco, yeah, California, and that's right on the San Andreas Fault. So I wouldn't be at all surprised that you're not right on the money there, that probably some of these places where there are these weaknesses in the Earth's crust or boundaries in the Earth's crust, these are places where you can access some of those minerals. I don't know if that holds for sick. Right. Yeah. Yeah. So, so yeah, it's I assume there's some connection there. It may be just happenstance, but it seems to be the case that, yeah, you would be more likely to find that in a place where you might have some of the faultings, okay, that we were talking about earlier in the chapter. Okay, now, trying to get, oh, I have to click on the screen sometime before, oh, there it comes. So here is the Richter magnitudes, okay? These are effects of earthquakes with varying magnitudes. On the Richter, a 0 to 2, they can detect them, but you don't notice them, okay? They see the lines move, but no one feels any shaking because these seismographs are very, very sensitive. So these are the smallest detectable earthquakes, okay, from 0 to 2, okay? Now that would be 10 to the 0, which would be 1, up to 10 to the second would be 100. So you have a range there of 100 times more powerful, the earthquake, but still they're so tiny you don't detect them. Then from 2 to 3, you can detect them and measure them, but usually you don't feel them, okay? Now, 3 to 4, felt as small earthquakes, but no damage occurs, okay? Now, did I relate to you that there was an earthquake in somewhere in Virginia, and I'm guessing this was about, I'm seeming to be stuck on 6 to 10 years ago. No, I think I can narrow it down. Yeah, 5 to 6 years ago maybe. And the reason I kind of can narrow it down a little bit, we had just recently built the house over in Georgia. It's just a 2-bedroom bungalow on the land that I inherited from my folks, because when we go over to work there, we were either having to stay with one of my brothers or sister, and they were pretty crowded already, so we just went on and built a house there. Well, I think the first Christmas after we built it, Karen, my wife's sister, gave her a thing to hang on the wall, and the house is on our farm, and just gave her this sign that said farm. Okay, it was sort of cute, but just said farm. So we had hung it on the wall. It was a big metal thing and just had a little wall hanger that it was hanging on. Well, we came home or went to the farm. I can't remember if it was summer when it was, and that was on the floor. And we said, why did someone take this off the wall? I mean, it wasn't bothering anybody. Well, when we said that to my sister-in-law, my younger brother's wife, she said, oh, that must have happened when the earthquake happened. The what? And the earthquake that had happened up in Virginia, down in Georgia, they had just barely felt it. They just felt a few things trembled, okay? If you'd have had a seismograph in Georgia, that would have been basically a 3 to 4 because no damage really occurred. However, closer to the earthquake in Washington, D.C., y'all know what the Washington Monument is? Big, tall obelisk that stands in the middle of the square in D.C. That had and has stairs you can go in and go up to the top, and you can see everything in Washington, D.C. from the top of the Washington Monument, because there's no building in the city is allowed to be taller than the Washington Monument. That's some sort of statute. So you can see pretty much everything in D.C. and much in Virginia and Maryland you can see from the top of the Washington Monument. Well, they had to close it because there were cracks in the wall, in the structure of the Washington Monument, and until they were able to verify that the repairs they had done were safe, they did. So that was not a 3 to 4 Richter magnitude earthquake in DC that was more like a 4 to 5. Probably where it happened in Virginia was more like a 5 to 6. I don't know. I don't know where it happened in Virginia, but it could have been. So the earthquake itself was a 5 to 6. But far away as Georgia, you only felt the small amount of damage. Closer to DC, you felt local damage. Okay. So, but the earthquake is what it is at its epicenter or at the focus of the quake, and that's the number they use. And they can extrapolate back to there, okay, because they have these all over the place. So 3 to 4 felt as a small earthquake, no damage occurs. 4 to 5, minor damage, minor earthquake with local damage. 5 to 6, a moderate earthquake with structural damage, and maybe in DC that was considered structural damage. Here's David. I think he's already been here, so he must have got booted out and come back in, or had to leave and came back. Okay. Now, 6 to 7, strong earthquake with destruction. Now, I can't remember right now what the size of the Haiti quake was. It seems like it was in the 5 to 6 or the 6 to 7 range, whereas the one in Chile was one step up from that, either 6 or 7 to 7 or 7 to 8. It was a much more powerful quake on the Richter scale. But because Chile had very, very strong, stringent building codes, much less damage occurred there. They had damage, believe me, they had damage, but not nearly the extent they had in Haiti. So Haiti's quake was not that strong. It's just the terrible building codes and no building codes that caused so much damage. The great earthquakes for total destruction, those are the 8 to 9. And like they said, the largest measured so far has been a 9. It seems like one they had in China recently may have exceeded 9. When this book was written, I think 9 was the largest. I can't remember the one on the Fukushima off the coast of Japan, what its scale was. It was a pretty powerful quake. And that was probably since this slide was printed anyway. So anyway, that's what you've got with that. Okay, any questions? Richter scale. Remember, those numbers, when you go from a 5 to a 6, you're not just increasing a little bit, you're increasing by a power of 10. Okay. Now, I can't advance until I click on the slide. Okay. And here is the same thing we saw before. I thought this was later. What we saw there, they show up in the slide here, which if I just waited, this is easier to read. But you can read it to your heart's content. Okay. Let me move on to the next slide though. No. Let's go back to the Richter scale. There's something I want to point out to you. This isn't in the slide set, but it is in the book, and it is important. This is on your page 490, well, my page 492. If you have one of the smaller books, it's 19-12. Okay? An increase of 1 on the Richter scale means that the amount of movement of the ground, remember that's what it measures, movement of the ground, increased by a factor of 10. So one number on the Richter scale, this is because it's a log scale, means the movement on the ground is 10 times greater than the one below it. Okay? But the amount of energy released increased by a factor of 30. 3 times 10. Okay? So that's the energy goes up by a factor of 30 for every one on the Richter scale, but the actual ground movement goes up by a factor of 10. Okay. So let's take a quick look at 19.5 in the book on page 492. Compare the energy released by an earthquake of magnitude 7.2. Now, guess what, folks? My wife ordered last week and I got it. It came in real close to the weekend, or maybe she ordered a week or so ago, but it came in last week, and it enables me to actually write, I think, on the slides. Let me see if, yeah, let's do it here. So what we have, well, the pad that I write on, let's see, yeah, there it is. Okay, you had a 7.2 on the Richter scale, okay, compared with an earthquake that was 5.2. And it's asking about the energy difference. Well, for every 1 unit that it goes up, that's a factor of 30. This goes up by 2 units because the difference between those two, if I can get it to show up here, is 2. The difference is 2. Multiply that by 30 and you get, no, I'm sorry. Yeah, I'm sorry. It's 900. Yeah. You raise it the power of 30. I mean, that's what I meant to say. I can't erase with this thing, or I haven't figured out how to yet. It's 30 raised to the power of 2, which would be 900. Every number that it goes up is another 30, and then 30 times 30 is 900. Okay, so 900 times more energy in a 7.2 than it was in a 5.2. Remember, a 5.2 is a fairly reasonable quake. It was a moderate earthquake with structural damage. A 7.2, major earthquake with extensive damage and destruction. 900 times the energy released. Okay, 19.6 is compare the amount of movement. Well, the amount of movement would then be just for every number it goes up, that's a power of 10, and it goes up the next number times 10 again, that would be 100 times the movement. Those waves on the Richter scale on the seismographs would be 100 times more powerful than the ones for a 5.2. Okay, so I did want to do that just to show off, and I mean not to show off my new device, but we do have it. But that's one calculation the book had that's a pretty reasonable one. Now, I don't know if you recall, I'm trying to remember now, no, I think it's coming up. In your text, the next thing that's mentioned here is a tsunami, okay? And that's a Japanese word used to describe the way a large ocean waves can be generated by an earthquake. And this is what happened in Fukushima. This is what happened in that really powerful quake that happened in Alaska. It was real close to the shoreline, and therefore there was enough underground movement that, if you can picture the ocean sitting here, there was enough underground movement, it created a wave in the ocean that traveled from Alaska to Hawaii and did damage on the islands of Hawaii, the northeastern side anyway. That was a very powerful earthquake. A tsunami is the water equivalent of a surface wave, okay, and they can be very, very big, okay. Obviously the energy to send it that far and do as much damage as it did thousands of miles away shows how much energy that earthquake had. That was a 9.0. At Fukushima, unfortunately, the earthquake was beneath the water. That tidal wave went up, tsunami, that's another name for it, went up and crashed into the, well, number one, the earthquake happened. That caused damage to the plant, okay, the power plant, nuclear power plant. And if I can't say for sure where was the chicken and where was the egg, but I think that the earthquake knocked out the power to the plant. Okay, it was a power plant. It knocked out the power to the plant. The tsunami, the water completely swamped the plant, which then, because the pumps wouldn't work, the emergency backup systems wouldn't work because the power was off, and that's why you wound up with such a huge nuclear disaster is what they had. Now they contained it because they did a much better job certainly than Chernobyl had done, and even we had done in 3 Mile Island, but it still was a pretty major nuclear accident. And an awful lot of radiation did escape and go into the ocean. They don't know that it went into, say, surface water or groundwater. I think they're monitoring very closely, but there was a lot of radiation that did escape, but it went into the ocean. And who knows what kind of effects we'll have from that for decades to come in fishing and things like this in those areas. It's not known, but that was a pretty major situation there. And I probably shouldn't spend too much time on it, but I do want to applaud the Japanese culture that was revealed because of that. This power plant, I mean, it was a major nuclear disaster. I mean, it was, but because they built it very carefully, it didn't cause that much damage, but there was major radiation leakage. Major. And they had to go in and secure the place. Well, here's what I'm talking about, the Japanese culture, how they're to be applauded. Some of the older Japanese men who had long since retired but had worked at the plant or worked at plants like that, they said, look, don't send any young people to that, let us go in. We're near the end of our lives. There's no reason for a young person to go in, be exposed to that kind of radiation, and come out damaged. Let us go in. And they did. And that to me spoke volumes of how tremendously sacrificial a lot of the Japanese culture is. You can't say everybody would do that, but the ones that did it, my hat's off. I mean, tremendous. Okay, too much there, but that was caused by an earthquake, and it led to a tsunami. Now the reason it's not showing up here, back when these slides were done, tsunamis were talked about in the Earth's ocean chapter. That's chapter 24 or something over there. So here they're talked about in this book, they moved them up to chapter 19. So we'll see the slide later, much later, when we do chapter 24, whatever the chapter is there. Okay, so let's move on to origin of mountains. This is beginning 19.4. All right. Mountains, the definition, elevated parts of the Earth's crust rising abruptly above the surrounding surface. Okay? And that's an interesting definition. It may not sound that interesting to you now, but it makes for some interesting comparisons. Okay? Does anyone know the tallest mountain on the Earth? Mount Everest in the Himalayan range. Okay? Range. Right up, I think, mostly in Nepal, but on the border of India, Nepal, China, it's right in there. The whole Himalayas are there. That's where the Indo-Australian crust is crashing into the Eurasian crust, and you get this buildup. So the Himalayas are still growing. Okay. However, by this definition, not quite, elevated part of the Earth's crust rising abruptly above the surrounding surface. Mount Everest is way taller than who I'm going to say next, Mount Kilimanjaro. Now, Mount Kilimanjaro is in Kenya, Tanzania, real close to the border there. But it is a fairly level area there that suddenly Kilimanjaro just sticks up there. I mean, that is a major mountain, okay? It's tropical at its base. There's used to be snow on the top. Okay, it's major. Now, Mount Everest is tall. It is really, really tall. But you see the whole Tibetan Plateau, and the whole country of Nepal is elevated. So Mount Everest just sticks up, by far the tallest mountain, but it doesn't stick up that much around the surrounding surface because the whole surface is raised. So sometimes when you're talking about mountains, your really tall mountains elevation wise are not the tallest as far as being above ground level. Okay. Now, how are mountains formed? There's really three ways. They mentioned two in this first thing here, created by either folding of the Earth's crust or by faulting of the Earth's crust. So you have folding mountains, folded mountains, or they have a name for it, but fault block mountains, they call it block. Okay, there's actually a third. The third is volcanic activity, where a volcano, the magma has come to the surface, become lava, and it's poured out and built a mountain around it. That's volcanic activity. Not folding or faulting, though a fault may have been involved. That's where the magma came from, but that's from volcanic activity. So there's the three basic origin of mountains. So let's look at each one separately. First, folded and faulted. We'll start with the folded. The domed mountains begins as a broad arching fold. And if it's an arch, what do we call that? Anyone remember? Anticline. Remember, it starts with A, anticline. The trough would be the syncline. That was earlier in the chapter. Okay? The dome mountain began as a broad arching fold, so it's a folded mountain, and the overlying sedimentary rocks, they get broken and cracked because this pressure coming from underneath stretches them at the surface, and they crack, they weather away, leaving the more resistant granite peaks, which probably came from deeper, exposed. So they may look sort of like they might be faulted mountains, but they actually were folded mountains. Many of the Appalachians are folded mountains. Okay? This is illustrating this. Now this would be eons and eons and eons of time elapsed before all this happened. The folding happens, the dome mountain happened, it's coming up very gradually, slowly. The surface, because it's stretched, is cracked, it weathers, breaks away, washed away, and then the harder underlying granite, those peaks come up. They're not as tall as what it was to begin with, perhaps, but that was what was creating the pressure in the first place. The one that's shown in the book somewhere, and maybe it's not this book, maybe it's the slide set, is Sundance Mountain, which, if it's the one the movie was named after, it's one of the best movies I've ever seen, but never mind, that's beside the point. Butch Cassidy and the Sundance Kid. Okay, but anyway, that's a folded mountain. Now, your fault block mountains, these rise really sharply and steeply along a fault plane. Remember, you have three different kinds of faults. You have normal faults, reverse faults, and thrust faults. Okay? Any one of these, one layer, either the footwall or the hanging wall, rises above the other. And that's what causes a fault block mountains. They rise sharply along steeply inclined fault planes. Okay? Now, over time, weathering does erode away the sharp edges, so you may have a fault block mountain that looks like a folded mountain, but it actually was a fault block, but it's weathered away over time. And that, again, is long periods of geologic time. Okay. Now, this illustration is showing it, and don't worry about the names too much, but this is, remember, your foot wall on the lower side. This is the hanging wall. The hanging wall is slid down the foot wall. That's from tensional forces in the opposite direction. That's a normal fault. Same thing here. The foot wall slid down the hanging wall slid down the foot wall, hanging wall slid down the foot wall, hanging wall down the foot wall. This is a fault block mountain. And remember, one of these is a graben and one is a horse, and I never can remember which is which. Yeah. At first, they were very angular and rise sharply. But over time, weathering occurs, wears off the edges here, and actually wears down the mountain, and at the same time filling in the valleys, okay? Because the weathering has to go somewhere, so it fills in down here, comes off the mountain, fills in here, so you have sediments formed. Okay, now that brings another dumb movie I saw. It was a fairly good movie though. Who was the guy, British actor who was in Pride and Prejudice and Notting Hill? I can't think of the guy's name, but he's pretty funny. And this was a little more serious role, but who's that? Hugh Grant. Yeah, you got it exactly. Okay, he was in a movie and it had an unusual name. So if you ever are playing charades, this is a really good one to use. The man who went up a mountain and came down, no, who went up a hill and came down a mountain. That's the name of the movie. And what it was it was in Wales, I believe it was, and they had not such tall mountains there, but there was a definite geologic definition for what a mountain was, how high it was above the surrounding terrain. And it was sometime after one of the wars, World War I or World War II, they went in and were doing their geologic survey, and they found out this community's mountain, they were named after that. I don't remember the name of the mountain, but it had a certain name, and that was their mountain, you know. But enough weathering had occurred, so the surrounding areas had actually elevated a little bit. They didn't realize they had, but they had, and the mountain part had actually deteriorated some. So when they went in to make the measurements, the geologic survey, it didn't qualify as a mountain. It was about 16 feet short of being a mountain. So they were going to rename it a hill. And they did not want their mountain to become a hill. So what they did, they started carrying sediment from the base around the bottom of the mountain, carrying it up to the mountain and building the mountain back again so that it would rise that 16 feet above that it needed to be reclassified a mountain. So Hugh Grant was the surveyor, and they talked him into hanging around until they could get the sediment back on top of the mountain, and he did, and he listed it as a mountain again. Dumb story, but that shows the reverse of what's happening here. Okay. Now we go to the third type, and these are volcanic mountains. And by the way, I wish they had the slide in the book, in the slideshow that's in the book. And this is a aerial picture of the Smoky Mountains, no, the Appalachian Mountains, and those are largely folded mountains. There's probably some faulting going on there too, but largely folded. If you got your book, that figure is figure 917 on page 1917 on page 1913, or if you have the big book, page 493. Okay. Now, here's another picture I wish they had in the book, and this actually goes, I'm going to go back a slide. This is faulted mountain. This is the Grand Tetons. The one in the middle is called Grand Teton. The ones on either side there are other Tetons. I don't know, they probably have names. But that rises abruptly off the plain. And this plain here, I'm pretty sure is what they call Jackson Hole. I think that's on the east side of the Tetons. And these are abrupt mountains in the Rockies that go way up above the surrounding uh, terrain. So these are very definitely fault block mountains. Okay, um, very angular, and they've risen up, and they're still growing, by the way, very slowly, but they are. Okay. Now, and by the way, they're only, I'd say, 40, 50, 60 miles or so from uh, Yellowstone National Park, which of course has a very major volcanic origin, and it's right on the continental divide. We'll talk about this in a later chapter too. So anyway, lots of geological things going on near the Tetons. Okay, now we move to volcanic mountains. This is on page 494 in my book, which is 1914 in yours. Okay, what is a volcano? Well, again, this could either be a hill or a mountain, okay, depending on how tall it is above its surrounding area, formed by extrusions of lava. Remember, lava is magma that's made its way to the surface. Extrusions of lava or rock fragments from the magma below. Because you see, it's not just made out of molten material. When a volcano erupts, it's quite often sends rock fragments that are not molten, not melted, into the air because it's broken through either the side of a mountain or the bottom of an old crater or something like that, and actually rock fragments are thrown up as well as lava is blown out. Okay, and then they say that the structure is the vent, the crater, and the lava flow. Well, they don't really go into what any of those are. They just say they're part of the structure. I'll try to give you my best guess because they really do a terrible job of this. This, by the way, is Mount St. Helens, I'm pretty sure. Mount St. Helens blew in 92 maybe? Trying to find it. I know it was in the book somewhere here, and it may have been an earlier page. Wait, here it is. It blew in 1980. 1980 explosive eruption. It was thought at that time to have been a extinct volcano. In other words, no longer active until it blew, and then it became an active volcano again. Now, would you think that a volcano would grow after an eruption, or would it shrink after an eruption? You would think it would grow, and most of them do. Mount St. Helens actually got shorter because it blew the top off. It literally blew its top. And so therefore that was around the top here, it was taller, but it blew that out. Okay, and that's where the rock fragments are coming from. Then you see the lava flows here. You can see them on all the sides of that volcano. Okay, did some pretty major damage. I think they said this picture was taken several years after the explosion, after 1980. So they don't say how long of several years, but you see none of the forest has grown back. That was a pretty major event. Now, certainly a lot of damage was done. A lot of economic damage was done. Okay, because it wiped out forests. It wiped out, and by the way, there's a lot of good apples grown in the areas around here. And even though it wiped out some orchards really, really badly, and this is far further from the mountain, like the ash that fell out of it, okay, on the surrounding areas, that did damage to those things when it was falling because it was hot, it was acid, it was just not good stuff to be around. But in subsequent years after that, the apples were far better because that brought up nutrient-rich materials from way down here and blew them into the apple orchards. Okay, so it's not all bad. Okay, not all bad. Immediately it was bad. It was really bad. But afterwards there were some benefits that came out of it. So yeah, sometimes Even though you would expect mountains to grow, sometimes they actually get smaller if they blow their top. Now, it's hard to say what are the things. I can tell you these are the lava flows. You can see where the lava came down, hardened, and left the appearance of a liquid that had hardened. Okay. The crater is this, obviously. That's right here. Now, it blew the side of the mountain off as well as the top, so that was a really major explosion. The vents would be places near that where, and these I think are just clouds, but if they are indeed water vapor coming out of the mountain, those would be coming out of vents. I just can't tell from the perspective they have here. Okay. Now, they go into three types of volcanic mountains. The first of these is called a shield volcano. I don't know why they call it shield, except that, shields are sort of rounded most of the time. They could be flat, but these are rounded ones, that sort of wrap around you and shield you. Well, these are constructed of a solidified lava flows with broad, gently sloping cones. Not a real obvious thing like Mount St. Helens. We'll get back to that in a minute. Here is an example of a shield volcano. Now, I can't remember which one this is. This is either Haleakala or Mauna Kea, or maybe, oh, it's Mauna Loa in the Hawaiian, in Hawaii, on the Big Island, I believe. That is Mauna Kea. Okay, definitely a shield volcano. Not a super tall mountain, very low, broad, gently sloping cones. Okay, these are the various craters that have happened over time, some big, some small, really small. Probably where they came out were what they call the vents. They never described this in the text, so I'm just making a guess there. Those would be the vents. The crater would be the big places here where obviously it left. Okay? And most of this is lava flow, just about exclusively lava. Now, I think I may have mentioned this before, but the most active volcano in the world, I think, is Kilauea volcano, also in Hawaii. The reason I say that, it has been erupting basically continuously for probably decades. Okay? Is it making a big mess? Not generally. It's not usually spewing out much lava at all, but it's almost continuous, just letting out the stuff. Now, a few years ago, I'm guessing about 4 to 5 years ago, maybe shorter, actually it started spewing a whole lot of lava and actually started doing a lot of destruction. So Kilauea got out of its sort of mild form and really started doing it. Just lava overran roads, it overran people's land, it just did whatever it wanted to because there's no way to stop it. Okay, now this would have been a great figure if they had wanted to show what event was. My guess, that's a vent right there. This would be the crater up here, but this would be a vent, a weakness. Oops, here's Capri. So let me get her marked in class. There you are. Every time I go to write, the pen won't write. Okay, Capri is here. Okay. And this is a shield volcano. All the rock here pretty much is basalt from rapidly cooling, small crystal size, fine grain volcanic rock. High iron content because it's coming from deep in the earth, and it comes up and excuse me, I meant to bring up a Coke and I left it downstairs. Some of this will find creases in the former lava flows and come out on the sides, but some of it comes out the top, and that would be, okay, I don't think anyone came in that time. My thing just came up at the bottom. I don't know why. Okay. but that's the shield volcano. Now the one they don't have a picture of in the slide set, but they do have one in your book, and it's a really neat picture. On page 496 or your page 1916 is Sunset Crater, a cinder cone volcano near Flagstaff, Arizona. You may say, wait a minute, isn't that way far inland for you to have volcanoes? And it sort of seems like it is. But you see these, the problem areas in the Earth's crust don't have to be along fault lines. They can just be in weaknesses of the crust, and this is one. Okay? And I wish I had a picture for what a cinder cone volcano is. It's constructed of mostly rock fragments, or those cinders. They're usually steeper, but also smaller than the shield volcanoes. See, the shield volcanoes are very, very gradual slopes, but can be quite large. This one is largely underwater, but still is quite large. Mauna Loa here is pretty large thing. Now, I don't know what that is in the background there. Probably one of the higher points on the island of Hawaii, but the shield cone, the cinder cone volcanoes they go up very, very sharply, and they're mostly rock fragments, not that much lava flow. Okay, and you can almost tell that looking, I don't know, it's not a great picture in your book, but it's a very distinct volcano, not at all like a shield. And then, sorry, I keep yawning. The third type, part of it is my head stopped up. I don't know why. Maybe I should turn off my ceiling fan. I think I will, if I can reach it. Okay. All right, sorry about that. Okay. And that's what they call the composite volcanoes. These are the ones you always picture. Okay. And it won't advance until I click on the slide now. There. And here's another. Oops, here David. He must have had to go out again, or it kicked him out. All right. This is a majestic mountain. And these are your composite volcanoes. Okay. Your crater's up here, usually near the top. This crater here looks like it's on the side, like maybe it happened with, whoops, two more people waiting. Who are they? Oh, David twice. Okay, I'll admit him twice. He's two of people. I did once. Okay. Now, I don't know why. Last time I did this and it quit. It's not doing it now. There we go. Like Mount St. Helens, the most recent eruption, I think this is Mount Shasta, if I'm not mistaken. The picture in your book is slightly different. It's the same mountain, but it's Mount Shasta, I think in Northern California. Yeah, a composite volcano in California, in the northern part of California. And what you can see in the book there is one of the more recent eruptions. It's pretty much, they call it extinct now, but that doesn't mean it will always be. It seems like it blew off the side of this mountain, but earlier it had been building over here. And that would be the crater. And again, it seems like to me these would be what they would call vents. I don't know if that's the actual right name for it again, but it has a mixture of alternating layers of lava flows with cinders. Cinder volcano is almost totally cinders or rock fragments. The shield volcano is almost totally lava flows. The composite volcano is made out of both. Alternating layers of cinders, which are rock fragments, and volcanic lava flows. Okay. Now, they say with volcanic mud. And that seems like a weird term there. Uh, and here's what my guess is, because they don't ever do a good job of describing this either. Mud is basically soil that water has hit and mixed in with. So I'm thinking what they call volcanic mud is where the hot lava actually melts the rocks that are already on the surface, and that makes the volcanic mud. This isn't lava that came from deep in the earth, but it's melted rock from the surface. Now again, that's my interpretation. They never do a good job of describing it. But this is Mount Shasta, and you can see here lava flows way, way from that original. That must have been quite an eruption that blew this off and gave you lava flows this far away. Okay. All right. Let's move on. We got 5 minutes, I think. Okay. Okay. Now, before we leave the volcanoes, there is a really, really good blurb on page 497, or in your book it may be 1917. Volcanoes Change the World. It's called A Closer Look. And it mentions several of the really, really major volcanoes that have occurred over time. Okay? And any one of these would be a good paper topic too. They mention the eruption of Tambora in Indonesia, and how much it affected not just Indonesia but the entire world. It spewed enough ash and stuff into the atmosphere, they felt effects of it half the globe away. Then they mention, in fact, after Tambora, in New England in June of 1816, there was enough ash. The Tambora erupted in 1815 to 1816. I mean, it was over, it was a long time, okay? Not 2 full years, but at the end of 1815 into 1816, it was erupting. It sent enough ash into the atmosphere that it blocked enough of the sunlight coming from the sun, made enough shade that in New England in June of 1816 it snowed. And if you picture, Indonesia's over here, New England's over there. Okay, I mean, it's almost half a world away. And they called it the year without summer because it snowed in June. It was so cold. Okay, there's in 1982, that was 1815, 1816. 1982 eruption of El Chicon, or Chicon, I guess it is, in Mexico. It was a very major one. Then in 1991, Mount Pinatubo in the Philippines blew, and it blasted twice as much gas and dust into the stratosphere as Chicon had done about a decade earlier. And much of that remained in the Earth's atmosphere for about a decade, the next 10 years. And it did cause cooling that was not normal. So volcanoes do change the world. They can be very major catastrophic happenings. But that doesn't mean uniformity isn't being held. They've always done that. So it's not just a single catastrophic event. All right, how are we doing on time? 2 minutes. Other features. Okay, here's the figure that goes with this. Not all magma makes its way to the surface. Sometimes this magma comes up underneath and forces things to happen. Remember that Dome Mountain? That more than likely was caused by magma pushing up, but it created a folded mountain. Now the magma that did come up after the erosion happened, the granite that was left over probably was a result of some of that magma making its way to the surface. So most magma does remain underground. it's fairly rare that you actually have volcanic explosions. Some areas it's happening all the time, but most of the time magma stays underground. It cools and solidifies to form some intrusive rocks. Okay? Intrusive meaning it cooled inside the surface of the earth. These are usually large grain, coarse rocks. Now some of the forms, landforms or features that form because of this, sometimes a baccolith. Okay? And this is what is shown here. Now remember that illustration of the Dome Mountain and then it eroded away and left exposed some granite? This would be the baccolith. It pushed up from underneath, but at the time it pushed up, it didn't break through the surface. This sedimentary rock that was on top was bent, folded, and then later eroded away because sedimentary rocks tend to do so, and they lost the pieces there, and that was the baccolith. The big, broad, large amount of crystallized magma, but it's underground. Now a stock is a smaller protrusion from a baccolith. See, a stock doesn't make its way later to be in the surface, but it does make its way up into the layers of the sedimentary rock. The baccolith intrusions can cause hogbacks. Now what that is where it's bent the sedimentary rock upward, and layers that were older now show up on the surface because it's been built. And this is a pretty rough area here, and that's why they call it a hogback. It's where exposed layers of sedimentary rock sometimes bound the layers of the igneous rock from the batholith. So it causes a hogback. That's another feature caused by the baccolith. Now, some of the other processes, a dike is a very small vertical intrusion. Baccolith is huge, broad. Stock is big, but not as big as a baccolith and doesn't go as high. The dikes are very thin. They make their way up and usually can reach the surface or not. Yeah, I know. Sorry about that. Someone's microphone's on that you don't realize it. I'm guessing maybe Scott or Caitlin. I see both of yours is on, but I'm thinking maybe Caitlin because yours is highlighted. Okay. Caitlin, I think this may have been coming from you. Okay, I don't know. Anyway, dike is a very narrow, thin vertical, whereas a sill is when the dike finds a weakness in the horizontal layers and you form horizontal layers of igneous rock. Okay, someone's microphone's on and you are bothering other people. I'm hard of hearing. It doesn't bother me as much, but okay. Now, the laccolith came out of a dike, but it got in between a layer, but there wasn't as much overburden, so it forced its way up and formed a little folded mountain here. Okay, so the laccolith is a small version of a batholith, you might say, but caused from a dike that came in between the layers and forced up a dome shape. Now that's a rough description of it, but this is in your text. Follow that. They give a little more detail than what I'm giving here. And I think that's the last. No. Well, we're almost at the last slide, but not quite. I thought we would finish, but we're not going to. So we'll pick up the overall picture next time. Okay. Someone's microphone's on. Sorry. Okay. Okay. So what I'm going to do is end the slideshow here. Yes. Okay. Let me see if this will do it. Yeah, that did it. It was Caitlin's, I think. Okay. That's a little better. Okay. We'll pick up and do the overall picture, which I think is the last slide next time. I thought we'd finish it today, but we just ran out of time. So I'm going to close this off, okay, and bring up, okay, oh, now David, you're in here, but you also are showing up as being joining. I know, but I'm seeing you outside and inside at the same time, so I won't worry about that. Okay. The screen sharing stopped for just a moment. What I'm going to do is go here and open Blackboard and walk you through how to get to the lab simulations. Okay. So I'm going first to. All right. Gonna try to get to black. Yuck. I don't know what's going on here. I think my Screencast-O-Matic just stopped, and I don't know why. Okay, it's still recording. I just can't see it now. Okay, so let me go to here. Scroll down. Okay, I'm going to Blackboard. And what I think I'll do is once I get in, I will pull y'all back in. I found this Blackboard somewhat awkward. Okay. All right, I'm going to pull up. I think this is where we are. Does it show well? Yes. Okay, can you see my Blackboard? Okay. All right. So I'm going to get this taskbar out of the way as much as possible. Okay. Now, I'll go down to this course. Physical Science 111. You probably don't have as many courses as I do. Here we are, summer 1920. That's us. Okay. Now we're in our class. Okay. There's the meeting today. I'm going to dismiss that. Okay. You can see this, right? Here's all the things I had. Okay. At the very bottom, you see laboratory simulations. Everybody see it? Okay. I'm going to click on that. Okay. Now, when it does come up, and sometimes it takes a while to come up, and it's not coming up like it usually does. So what I'm going to do is, okay, go over here to simulations. You see that? And that gives you an option. I'm going down to Earth Science. Can you see that? Okay, click on Earth Science. Now, we see the whole family of Earth Science things here. These are listed sort of alphabetically, so you just have to scroll through. We don't want balloons and buoyancy and those kinds of things, diffusion. These are all interesting, good stuff. There's a thing on glaciers. We might come back to that in a later chapter. Gravity, force basics, okay. All like there's my solar system, which probably would have been an interesting one, but we had others to do there. And by the way, I'm going to show you now. These most people can see, okay. These I think most people can see. These that look like a coffee cup, those are ones that people have trouble seeing. And unfortunately, the one we're going to do now is that one. And basically here it is. It's the only one they have on plate tectonics, and it's a coffee cup. So that's, unfortunately, you may or may not be able to do it. So what we're going to do is open that one, click on that, and then you come up here to the arrow that's inside that and click on it again. And that it says down here, this type of file can harm your computer. It doesn't seem to do so, so I'm going to keep it. Okay, and I have to wait a little while till it finishes loading. I think it has. Let me see. Now it's trying to open it. Okay, so we're here, open now. Okay, now I don't have the printout. I have what I wrote on pieces of paper, and that's what I did the printout on. And basically what it said was go to Blackboard, go to the course content, which we did, go to lab simulations, which we did, click on simulations, that was over on the right hand side there, go down to earth science, we did, and then the plate tectonics. You have to scroll down to get the plate tectonics. Okay, now I can't read my writing here. What's the next thing it says there? Click on what does it say? Okay, I just did that. Okay, lower right it should be, but I must have done it wrong. Okay, that's what. Okay, so click on both. You see the view box down here is lower right, not lower left. Sorry about that. Click on both. Okay, I clicked on it and oh, there it goes. Okay, and also show labels. Right? Did I say that? Yeah, labels. Okay, now you see what's called. Now, what we're doing here, just to give you an idea, here's the oceanic crust over here. Notice it's thinner, and oh wait, for some reason it paused. Sorry, let me get it back again. Come on. It's coming up in increments. Sorry. We were sharing, sometimes it quit sharing. Okay, so new share. Okay. This is really slowing down my computer like crazy. Okay, can you see that now? Oh, okay. So here was the lower right corner, view, both, and show labels. Okay, let me take you back. See, before I did show labels, you didn't see the various things there. We're going to do density and temperature, so we did both, and I also want to show the labels. Now my computer is slowed down really greatly. All right, now what we see over here, here's the oceanic crust. Okay, it's thinner but denser than the continental crust. Continental crust is thicker, and as you'll see later, not as dense, not as dark. Okay, so what does the next thing it says to do? Click on lower left corner. Okay. Can you, okay, after it says, right, okay. Okay, so we're going to start with the continental crust. So what I'm going to do is increase the thickness. So I have to put my tab on that and move it over, and you see it's making my crust, which is the one here, thicker. Whoops, 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 whoops. Too thick. Okay, whoops. Now, there's a way to make them even at the top too, and I haven't quite done that. Composition, I'm going to do more silica because see, it's darker than the continental crust. See, the crust, my crust here, so I need to do its composition more towards silica. And when I do that, you see the top rises. Okay, there. But now I'm not at the bottom, so I'm going to do increase the thickness ever so slightly, and there. Oops, I might need to cut off the silica a little bit. Okay, and decrease the thickness just a tad. Okay, that's pretty close, isn't it? Okay, that I think I have continental crust here. Okay, now I think what it says to do next is get in the toolbox your ruler. Is that right? What does it read next on? Okay, get the toolbox. Okay, that's what we got here. And that looks to be in kilometers. It looks right around 45 kilometers deep, right? Thick. 45 kilometers. Multiply that by 0.6. Let me get my calculator here. This is a rough approximation. You don't have to do this. I'm just doing it for your own cultural enlightenment. 45 kilometers times 0.6 would be about 27 miles. That doesn't sound very thin to me, but that's how thick in general the continental crust is. Okay, so did you record that? Is that the first thing to record? Okay. Right. And what would you say? Silica. Yeah, the composition is more toward the silica end. Okay. What's the next thing? The density or temperature? Okay. Pull up the thermometer. Now, this thermometer is on, I don't know what kind of scale it is, but what we're going to call this is, let's just call that the first line there 10 and the second one 20. Okay. It's not going to be exactly that, but let's just say it's registering at 20 now. 20 degrees Celsius is room temperature, so we're just going to say that. So that's the top of the crust. Does it say go to the bottom of the crust too? What's the next thing it asks for? Lower part of the crust. And do you see the temperature is going up? My goodness, you go 27 miles down, you better figure. I'm just going to estimate that's about 30 degrees Celsius. Now, I'm just making up these numbers. Let's just call it 30. Don't put degrees, don't put Celsius. Just call it 30. 20 at the surface, 30 a little bit deeper at the bottom of the crust. Okay, is that all I ask about temperature? Now density, is that next? What's next? Move the density meter. Okay, and we'll first put the density meter near the top of the crust, and let's just take a measure there. Let's just call this 1, 2, 3, 4, 5, 6, 7. Let's say 7.7. That look good to you? Yay or nay? Okay, about 7.7. Okay, yes. Well, there it is on the ruler right there. 45 kilometers. You see it? Okay. So density near the surface is, what do we say, 7.7? You okay with that? Okay. Let's take the density meter. Do we take it toward the bottom of the crust? Okay. Yeah, because the density didn't change, so I left that off. Okay. So now what we're going to do is change the thickness of the crust, just like Roy was saying, until it matches the oceanic crust. So that's taking the thickness much, 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 much thinner. Whoops. Now I need to do a little bit with composition here. What I'm doing with composition is trying to match the color. And you see it's getting closer to matching the color. Do you see that happening? I think I'm really close, don't you? Can you see that? All right. Now what's the next question to ask? And what do you say? It moved from over here on the continental crust to over here. So more on the iron end, isn't it? Do you see that? That's what I was moving. Okay. Of the oceanic crust. Okay. So let's lower this down here, get to the bottom of the ocean. And what would you say? That looks like about 7 kilometers deep. That's not very much. That would be about 4.2 miles or so. Still pretty thick, but you know, much thinner than the continental crust. Right? Okay. Did we move the thermometer? Okay, the thermometer near, oh, density meter. Okay, let's do the density meter first. To the top of the, I think it's just anywhere in that, isn't it? Does it say just anywhere in the oceanic crust? Okay. All right, I got it there, and it looks like now we're at, that was 10, 20, 30, 40, 50, 60, 70, 80, looks like about 8.5, would you say? And what was it in the continental crust? About 7.7? Okay, so you see the oceanic crust is much denser, more iron content. It's mostly basaltic. The continental crust is more granite. Okay. Now, did we do temperature now or not? Okay, and you can answer those questions, can't you? Yeah. Continental crust thicker, but the oceanic crust denser. Very good. Now, does it say now go to the zoom box? Or is there a question there? I think there is a question. Isn't there a question like what's the boundary between the crust and the mantle? Or is that coming up later? Okay, and what is that boundary called? Oh boy, you got to look that one up to spell it too. If you want to just call it the MOHO, that'll be okay. It's actually called the Mohorovicek discontinuity. You can look that up in your book and see how to spell it, or you can just call it the MOHO. Was that the next question? Okay. All right. And then does it say go to the zoom box? Okay. So let's drop this down to the upper part of the mantle and see what the temperature is here. Now, did it say do anything with the crust? Or are we leaving the crust alone now? Okay, now look at, yeah. Okay, so let's say, remember I was saying this is like 10, 20, 30. Now it looks more like 40. So it looks like the mantle is warmer than the lower part of, than the crust was. Would you say? Now again, these are relative temperatures, so don't put any degrees on them, but just relative. Whereas the crust was around 20, this is around 40. Okay? Now what? Zoom or not? Oh, move the density gauge to the upper part of the mantle, right? Okay. And didn't seem like it changed much, did it? Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Looks like maybe 8.2 or 3 or something like that, would you say? Read the question to me. Move the density. Okay. Looks like maybe about 8.2 or something like that, would you say? Okay. All right. Now what's next? All right. Now we go to the zoom. Not a boom box, but a zoom box. Okay. Now what we're going to do is pull this down, and you see where our ruler gets thicker too. Okay. And does it go all the way until you can see the boundary between the upper and the lower mantle? Does it say that? Okay. Yeah. And what is that boundary called? Anyone remember that one? Asthenosphere. Aesthenosphere or something like that. You'll have to look up in the book to get the right spelling of it. That's the asthenosphere. Okay. Now, have a little bit of problem here because my ruler's not long enough to do a good measurement, so I'm going to have to zoom down a little bit more just to get, there we go. Now, we got it. Now, what's the first question it asks after we zoomed and after we identified that layer? Okay, surface to the boundary. Okay, now I'm going to move my thermometer out of the way a little bit and move the density meter out of the way a little bit. Okay, I'm going to move, I think I'll go back slightly into the continental crust here. The surface is right about there to the boundary. What would you say, 750 kilometers? You see it right there? Yeah, 750 kilometers. So the upper part of the mantle way, way, way thicker than the crust ever dreamed of being. Okay? And you're just part way into the mantle. This is the upper part of the mantle. Okay? Now, is the next question, how thick is the upper part of the mantle? Ah, and what is that called? When you add the crust to the upper part of the mantle, right when you get to the asthenosphere, what is that layer called? The sum of those two together means the rock circle. In other words, lithosphere. Lithosphere, I think. You have to check the book to get the right spelling. Lithosphere. Does that sound like it rings a bell? Okay. Then the next question. Okay, so this time we take the ruler and move it down just a little bit until you're at the bottom of the crust. And then that's only about, oh, what, 700 or 710, 720, something like that. 710 kilometers. And that's from the bottom of the continental crust. That's where we live, so let's use that one. Okay. None of this is exact. These are all approximate. Okay. What's the next thing it asks for? Okay. Is that the upper mantle? boundary with the crust or upper mantle boundary with the lower mantle? Can you tell? I think we already did this one. That was around 40, wasn't it? Okay. Okay. I think that might mean over here, this boundary. Now what are we up to? We're saying 10, 20, 30, 40, let's say 52, something like that. These are just relative, okay? Okay, now the upper part of the lower mantle, and 10, 20, 30, 40, 50, looks like maybe it went up a little bit, 54 maybe. So there was a little bit of an increase in temperature there, okay? What next? Density? Okay, it's coming down. Oh, I didn't ask for where did it reach 100, huh? What you might say, throw this in there, the density meter went to 100. You see how it pegged out and then went back over here? So it went to 100 right around 250 to 275, something like that. That wasn't in there, huh? Okay, it's okay. All right, but remember, now we're measuring this is 100 and some. So let's keep moving down, down, and you see the density keeps going up, 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 up to the lower part of the upper mantle, right? That right? Okay. Do I seem like I have it about the right place? Okay. That would be, remember, 100 from here. Oh yeah, 1. I'm sorry. 1. Okay. Those were, yeah, that was a 1 here. Okay, 1. So this would be 11, 12. Right. Okay. But this got me up to 1. And now we're starting over again. So this would be 10, 11, 12, 12.6. And again, these are just relative numbers. But you see, we've already pegged out the scale at 1. And now we're, say again? Okay, well, okay, let me back off. Was I saying 1 point something or 7 something? Yeah, I was doing that. So this would then be 10. So this would be, that would be 10, 11, 12. Let's call that 16. Because my earlier one was like 8 or something, wasn't it? What's the last density you had before this one? Huh? Say that again? 8.2. So this would be something like about, that would be 10 when it got here with 10, 11, 12, 12.6. So the density has gone up significantly. Now again, these are relative numbers. These don't have any units with them. Okay? Is everybody following? I hear from 2 people. I hope the others are following too, right? Good, good. Okay. What's next? Are there questions? Be sure to ask questions if you have them. What's next? Huh? Okay. Okay. So we're going to continue down through the lower mantle until we get to the outer core. Whoa, it's way down here, isn't it? Oh, there we see it. But I have to keep going until the ruler expands. There we go. Okay. So, and what was it, from the crust or from the, okay, it didn't say the bottom of the crust, just the crust. what I'm going to do is take the ruler and move it up to the surface. Or does there another question like that? I think we'll just move it to the surface. Okay. And what is that distance? It's 2,500 kilometers. That's 2550. No, that's 2750. So this looks to me about 2,800, would you say? 2,800 kilometers. Notice now, it doesn't matter what the crust is. These are such huge numbers, the crust doesn't even count anymore. See how thin it is? There's the continental crust there, and somewhere there is the oceanic crust. They're just so thin, they don't even matter. Okay, so this is about 2,800 kilometers to the outer core. Is that what the question was? Okay, what's next? Okay, so we will go to the bottom of the crust, and that would be maybe 2,700? No, I think the last one probably should have been, well, I don't know. There's not much difference. This looks like 2,700. What did we say? What was the last answer? 2,800? Okay, let's make that 2,900 the last one. This is 2,800. Okay, I was doing my scale wrong. It's it's the crust is insignificant now. It's just so small it doesn't make much difference. Okay. All right. What's the next one? Okay. Let's see if we can. Oh, here we go. Take the ruler. I'm going to move these meters out of the way because they're sort of clogging up things here. Okay. Let's move the meter down here to lower mantle to the outer core. Yeah, outer core. Somewhere right in there. That looks to be about 2,400. Thickness of the lower mantle looks to be about 2,400 kilometers. Would you say? Okay. Okay. What's next? Okay. Okay, yeah, that now is when I move to the surface. Okay. Now I'm on the surface and move the thermometer till it reaches 100. In other words, you'll see when I'm talking about. Whoops, right about there. Would you say that's 1,250 kilometers? Say again? No, no, okay. No, okay, wait. I'm counting when this popped over, I'm just going to call that 100. I know they're not 10 of those, but just to have a relative scale. Let's just, yeah, yeah. So right around 1,250, 1,250 kilometers. These are all relative, nothing special here. Okay? Does it say keep on going down? Say that again. One more time. Oh, you're in the lower mantle, aren't you? Is that what? Yeah, lower mantle. Okay, our ruler's sort of blocking the division there. Let's see. Okay, and yeah, you don't have to put degrees. I probably did, but yeah. Okay, we're going, go down. The temperature is going up, 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 up. Now these are just relative. Whoa, there we have it. So what does it ask? The depth? 2750, exactly. Is that what the question was? Oh, and the region? Still in the lower mantle. But you're in the lower part of the lower mantle now. But you don't have to say that. You're still in lower mantle. Okay, what's next? I said 2000. If you can see the screen, it says 2750. Oh, I see. Okay. Right. 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 Yeah, I was afraid of that because, see, I don't have a copy of the lab, so I'm not filling out the lab. I have my earlier writings on it, but it's pretty cryptic, so that's why I'm asking you to read it to me. So yeah. So ask questions. By all means, don't let us go too fast here. Okay? Any other questions before we move on? Okay, what's the next one?
Question 27. What is the temperature in the lower mantle just above the outer core?
Okay, let's move on down to there and see what we get to. Okay, that would probably be good. I'd say 220, just to round off somewhere there. See, these two, I'm calling 200, and that'd be another 20. Again, these are just approximate.
Question 28. What is the temperature in the upper part of the outer core?
Okay, we're going to go right below that. Whoa, and did you see it jump? It went to 230 plus. I'd say 232. Again, relative numbers. These aren't real temperatures. They're probably more like 2,300 and something, but we don't have a scale to go by, so I can't. So just using this as a relative scale, it did jump up when you cross that boundary. Okay?
Question 29. What is believed to be the phase of the outer core?
Okay, when I say phase, that means solid, liquid, gas, or plasma. What do they think the outer core is? No, not plasma. That would be in the sun. We're not that hot. The outer core they think is liquid. That mantle was all solid pretty much, except in that asthenosphere, remember in between the upper mantle and lower mantle, right below the lithosphere, in there they have pools of semi-liquid material. That's probably where most of the volcanic material is coming from, not way down here in the outer core. Now, I guess it could make its way through the lower mantle, but look how thick that is. So the outer core is believed to be liquid. Why? Because your S waves, your seismic waves, the secondary waves, the transverse waves, they won't go through a liquid. And remember that shadow zone? Nothing gets past the outer core in the S waves. In the P waves, yeah, they go right on through the outer core, the inner core, and then they make their way on to the out the other end. Okay. It does have a shadow zone, but not like the S waves do. S waves. Okay, so the outer core is believed to be liquid. What's next? Okay, let's move it down and see what's happening here. Okay, density is going up, 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 up. The lower part of the lower mantle, right? Okay. Now, what were we saying before? That was 10 was the first scale. So this is 11, 12, 13, 14, 15. Looks like right around 16. So it's gotten quite a bit denser. And again, these are relative numbers. That could easily be 160. I have no idea what this meter is supposed to be measured in. Okay. Okay. So I'm going to go a little bit further. Whoa, did you see that jump? Now that's unbelievable. Watch it again, if you can see my screen. See, here it was 10, 11, 12, 13, 14, 15, around 16. Oh, and when you jumped across there, it went all the way up to 20, and now 21, 2, 3, 4, 5, 6, 7, 8, 2850. Well, I'm not even in it yet. Okay, let's say 2900. 20, let's say 2900. We're close to 2900. Wow, enormously increased density. And yet it's a liquid. Say that again. That's probably part of it, but just all that pressure on it from everything above it is weighing down on it. So it just makes it much, much denser. And probably the liquid nature contributes some. Okay? What's next?
Question 32. Expand the zoom to the max and move the ruler to estimate the thickness of the outer core.
Okay, all the way to the max. Okay? Now I can't get my ruler to grow any, so we're kind of stuck. So move the ruler to what? Thickness of the outer core? Is that right? Is that what you said? Okay. So let's do the thickness of the outer core. See how I'm moving it down? Yuck. I can't quite get there. Okay, since I can't get there, I'm going to put the 1000 at the edge here, and the outer core goes down to here. Let me move this over a little. Okay, so let's count. That's 500, 1000, 1500, 2000, 250. Yeah. The thickness of the outer core looks to be about 2,250 kilometers thick. Man. Do you see that? Radius of the inner core. So I'm going to bring the ruler up. You see the inner core there? So I'm going to bring it up here. So we're going to have to estimate from there to there. Okay, so that's 500, 1,000, 1,200 maybe. 1,200 kilometers, 1,200 kilometers. That's my guess. Y'all figure that's close enough? You see it? Because 5,000 is at the end here, and we go past 4,000, so that's going to be 1,000, but not quite 250, so I called it 200. 1,200 kilometers, which is awfully thick. Okay, and I think that's what they're showing here. This is the center. That's not the outer edge. Yeah, see, it goes all the way around, yeah. So I think that is. I puzzled on that myself, but because this doesn't look like it's decreasing here or on the other side, I think this is the center right there. It took me a while to figure all this out myself. Okay. Lower part of the outer core. Okay. That would be right about there. So we're calling this 200, 10, 20, 30, 40, 50, 60. Let's call it 270. I mean, just to have a relative number. Would you say that's okay? Okay. Again, it's nothing precise, just relative. 270. Probably 2700 or something like that. So I don't know what scale they're using at all. What's next? Okay. Near the center? Alright, we're right at the center, I think, there. And it looks like 2, 10, 20, 30, 40, 50, 60. It moved up. If you said 270 before, say 275, 280, something like that. It did move up. I saw it go up. And again, I don't think this is very precise. Anything about this is very precise. But it did get hotter and hotter the deeper you go. Now, did they ask the question about the phase of the inner core? Did we skip that, or have we gotten there? Okay. So I don't know. I can't remember why I moved the ruler up, but I will. Okay, move the density meter down until it exceeds 300. Oh, I know why. Yeah, I know why. Oh, there it went. Okay, let's get over closer. All right. That's probably too close. Okay. Let's see what we got. 3,000, 3,250. So it jumped up there. 3,250, 3,300, something like that. Kilometers down. Is this making sense? No, no, okay, no. The density where it crossed 300. See, 1, 2, 300. Or, no, we were calling this, oh, tens. Okay, 30. When it passed 30. Okay. What was the depth there? 3,000. This would be 3,250. 3,300. Just a good estimate. We're nothing precise here. Is this making sense? Okay. What's next? Lower part of the outer core. That's right about there, isn't it? Okay. Now we have, this was 30, 31, 32, 33, 34, 35, 36, 36 and a half. Look about right. And again, these are just relative numbers, but you just see the density is going up, 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 up. Okay. What it was, I ran out of paper. I didn't want to do another page. Okay. But let's just take a look, and if you want to write this down, you can. It would be sort of, I did want to ask, I thought I asked it, but I must have forgotten it. What is believed to be the phase of the inner core? This is just for your cultural information. The inner core they think goes solid again. There's so much pressure it can't even maintain as a liquid. It becomes a solid. Okay? Let's see what the density does when we cross over into the inner core. Not a big shift, but it still gets denser. Okay, let's go to the center and see what it is. It's still getting denser, but you don't have to record this. Okay, so it just keeps it getting denser the further you go. Okay, all right. Anything else that you would like to investigate while we're here? Questions to ask? Now, frankly, they called this plate tectonics. There was absolutely nothing about plates except sort of what the crust were, okay? But the plates are all in the lithosphere. They float on that asthenosphere. And I'm going to move the ruler out of the way. Remember, the asthenosphere is this boundary right here. And the plates float on top of this. Everything here is solid rock all the way around. This is liquid all the way around. This, let me move these out of the way. This is solid again all the way around. I can't go to the bottom half because the thing comes up in the way. Okay, but the plates are all above the asthenosphere. This boundary between upper mantle and lower mantle, that's the asthenosphere. The plates float on that. It's a semi-liquid material, that asthenosphere, with quite a rapid change of density there. I think we measured that. So that was where plate tectonics fall. They didn't really make a big deal about it, but that's where it was. Now, the second half of this, and we didn't do it, this was plate motion, and I could never get this to work very well. So that's why I left it off. They just show, and I can't see much of anything they're showing. And so therefore I left it off, so we didn't do anything else. It has an automatic mode. I don't know if I tried that. But I never could get anything to happen. So this is where I thought maybe this is where it might damage my computer or something, so I quit. So I couldn't get anything there. But I thought what we had. What did y'all think of the first part? Did it give you any insight? You don't have to say yes. Okay. Okay, you think what? Something about different answers. I missed that part. Okay. All I'm looking at is relative. Okay. As long as you're using the same scale everywhere, yeah, you may have called it 70 where I was calling it 90. I don't care, as long as you're showing the temperature going up as you go down, the density going up as you go down, the thicknesses should be fairly close, okay? But, probably not exact. That's okay. This isn't an exact science. It's not perfect spheres. They're jagged. They're ragged, okay? The continental crust isn't the same thickness. Some places it's thicker, some places it's thinner. The oceanic crust, at the place where you have the mid-Atlantic rift, the magma's coming right up to the surface then. So so there's no exactness here, okay? They should be all over the place, okay? Because different places that it would be different. But I just wanted you to get kind of a visual picture of what it is we've been talking about. Okay? Did you feel like it gave it to you? Okay. Look at that tiny little crust up there compared to what we feel like. And what was that? Miles and miles and miles deep. It just shows how thick, how huge the earth is, okay? And whereas on the surface we think those rocks are pretty dense, 400 times denser deeper down, or pretty close to it anyway. It's just huge ranges of magnitudes here. You all right with the lab? Did you have any questions or issues? I'll be glad to stay with you, because I'm not sure all of you can pull this up, but if you can, go and do it yourself. And if you want to come up with different answers, it's fine, but they better be consistent, making sense. All right. You want me to do anything else? Show you something else again? I'm here at your mercy. What you think? Any more questions, issues, comments?
Just to be sure, we're up to test number what?
Okay, let me think. We had 3 tests in astronomy. That's chapters 14, 15, and 16. And then we had test 4 was rocks and minerals, and test 5 is plate tectonics. And the chapter we're almost through with now is will be your test 6, and that's the what is the name of it? Building Earth's surface. And building Earth's surface, that test is going to be considerably different from the others. It's going to be a one-sheeter, but have several fill-in-the-blanks. So it's going to be a bit different from the other test. Not nearly as many multiple choice, though there may be some, but it'll be more fill-in, because when I got to the test bank in that chapter, oh my word, it was awful. I thought they were used such nitpicky questions. And I thought, who even cares about this? So why make students try to distinguish some of this? So I rewrote the better questions and put them as fill in the blanks rather than multiple choice. So you'll see that. I'll probably post it after class next time. I've got to work up the lab for next time, because we'll be finished chapter. I just can't remember what the lab was. Well, I can look right now. But the lab we had for this one, what it would have been had we been in class, we would have gone down to a lab and measured the density of granite, the density of basalt, and that would have been the lab. You'd have been filling out all that information, and we couldn't do that. I mean, there's just no way we could do that here. So let me see what the next, I think the next lab after this one, let me just see, is called latitude and longitude. And let me just make sure. Yeah, density of igneous rocks would have been the last one. This one had densities in it, but not exact numbers, okay? And then next will be latitude and longitude. I think, since all of you have computers and cell phones or smartphones and things like this, I think we can make up a good lab. I don't have to come up with something like this, because it took me hours to figure out what the best thing to get a lab out of this was, and then to type it up and stuff. It was a long, grueling process. But I knew we couldn't do a physical lab measuring density. We couldn't do it. No way. So that's why I did this one. So latitude, longitude is what we'll do next, I think. And all right. All right, any questions, comments, anything that you need me to go back over on this lab? Oh, y'all let me go past the time that we're supposed to call roll again. Valerie, you're supposed to be keeping up with my time. Okay, let me go back. What's that? No, 4:15 wasn't lab time. It was 4:45, remember? And now I'm afraid some people have left. But let me get, I know Roy's here. I know Valerie's here because they've been answering all the questions. Capri is here. Is David's here. Okay, Cormisha's here. There you are. Okay, Harry's here. Juan's here. Nikaya's here. Okay, Scott's here. I know Scott's here, but I can't find him. There he is. Okay. Thomas is here. Okay. Let me go over the ones I don't see. Did we lose Don? I think we lost Don. Did anyone see him here while we were doing lab? Okay. Caitlin. Was she here part of that time we were doing lab? I know she was here when her phone was on, but I don't remember if she stayed after we started doing lab. So I think those are the only two we lost. Okay, so we wound up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. Okay. All right. Any other questions, issues, concerns, problems? I hate to cheat you out of, goodness gracious, more than 30 minutes of your tuition dollars. Oh, more than 45 minutes of your tuition dollars. Okay. Are y'all okay with it though? You gonna write me up? Just kidding. Okay. All right. Okay. Anything else you want to do? Talk about, see, go back over any of it? Uh, I I checked them last evening after I finished teaching, but I haven't checked them since last evening. What was the nature of the messages? Okay, a question about it, or you turned it in? Oh, okay. Let me see if I printed it this morning or last night. And this is Cormisha asking. I got something from Don. Other classes. There's something okay. Uh, looks like most of what I got was probably before you sent it because, yeah. I got something from Scott. I printed that last night or sometime recently anyway. But no, I'll be checking again tonight. I've got a meeting with the dean. It's going on right now, but as soon as I get off here, I'll be in that meeting. And then whenever that gets over with, I'll be checking and seeing if I can print those things. I haven't had a chance to grade any lately, but I'll try to when I can. Right now they've got piled up on us. We're trying to work through fall schedule, trying to do evaluations for our faculty, and there's something else that we're trying to do now, and then I'm trying to teach and keep up with grading, and it's just about to run me crazy. So it's probably going to get a little wacko for a while. Hopefully I'll get caught up sometime. What made it worse is my wife and I were working on our taxes this weekend, so I didn't have a lot of time to do things this weekend either. So that was my bad, but couldn't help it. All right, any other questions, issues, concerns? Do you want to continue this any longer? I want to clear up anything you got before we shut down. So Anything? All right, let me know something, somebody. Want to go and stop the sharing? Okay. All right, so I'll stop the sharing, and then if I don't hear any objection, I'm going to end the class. I've still got to find the recording. I don't know where it is, but I'll end the class, end the meeting for all. So take care, folks. We'll see you on Wednesday. Okay. Bye bye.